Differential equation has two broad classifications. One is differential equation of first order. You all know what we meant by differential equation of first order. The general form may be taken as this: dy dx plus py equal to q. And another form, this is actually linear differential equation of first order and first degree. And another format is m dx plus n dy equal to 0, where this m and n are functions of both x and y. Obviously, we can apprehend that this form includes equation of first order as well as not first degree, because this y may be of some higher degree, and we may include nonlinear equation in this category. Okay, and then we have the broader version of nonlinear equation written as f x y p equal to 0, where p is represented in place of dy dx. So this is the broad category, any function of x y p of nonlinear equations, and this can well be then classified in three broad categories, in which the first one we can express y as a function of x and p. The second one, when we can express x as a function of, say, y and p. And the third one, where p is written as a function of x and y. Okay. And in this first category, we have the so-called famous clairaut's form, which is written as y equal to px plus fp. So these are the broad categories in which we can classify differential equation of first order. This is the most general form of differential equation of first order and first degree, where obviously it is tacitly assumed that p and q are function of x alone, because if there is y, then we come to this form where m and n are function of x and y both, and which includes nonlinear equation. But this is also of first degree. This is also of first order. This is also of first order, but it may be nonlinear, because we may have p square or y square or y cube, this type of terms, which makes it non-linear. Okay. So when we say a differential equation to be non-linear, when it includes non-linear terms in terms of the dependent variable y and p dy dx, and these non-linear equations are these three broad categories: one where y is expressible in terms of x and p, other when x is expressible in terms of y and p, and when p is expressible in a linear form of y and x. So let us get back to this most structured form, dy dx plus py equal to q, where p and q are both function of x alone. P and q are both function of x alone. we can easily establish that in this case we may have as integrating factor e to the power integral p dx. This is the integrating factor. Now what does it mean? It means that when we multiply this equation with this factor, when we multiply this one equation with this factor, it becomes integrable. Actually, we would prefer to have it in this form. Only in this form we have integrating factor this, and so we have this when we multiply it with the integrating factor. This can easily be understood that this term is nothing but ddx of y e to the power integral p dx, and hence obviously when we write it in this form it becomes integrable. Isn't it so? This is the total differential structure d of this, and when you integrate it, it becomes this equal to integral q e to the power integral p dx fx. Okay. So let me explain a bit. We can write it as e to the power capital Fx, and from fundamental theorem of integral calculus we know that whenever integral p dx is fx, we have df dx equal to p, where p is a function of x. Isn't it so? So we write it as e to the power fx plus, so p is replaced by df dx, p is replaced by df dx, so it becomes this, isn't it so? And obviously if we write it as so, this is comprehensible, because when dy dx e to the power fx stands apart, and when y stands apart we take the derivative of e to the power fx with respect to x, it becomes df dx into this. So this is this, and when we integrate the first integral it gives this. So this is the solution of this equation is given by y equal to e to the power minus integral p dx into integral q e to the power integral p dx, and if we replace e to the power integral p dx by e to the power fx, it comes out to be e to the power minus fx integral q e to the power fx dx. So whenever we have a differential equation of this form, first order and first degree, we have e to the power integral p dx as its integrating factor, or which makes it integrable. It takes us to another very particular form known as Bernoulli's form. Okay, this form is known as dy dx plus py equal to qy to the power n. This form is reducible to the previous form. How? If we divide this y to the power n, the left hand side becomes this, and then if you replace y to the power 1 minus n by z, we can easily get that dz dx is nothing but 1 minus n y to the power minus n dy dx. Isn't it so? And we replace y to the power minus n dy dx by 1 by 1 minus n dz dx plus pz equal to q. So this takes the form this, and since 1 minus n is a constant, so it is comparable with the linear form of differential equation dy dx plus py equal to q. This is replaced by p prime and this is replaced by q prime. Next, we will move on to illustrate about the special form y equal to px plus fp, which is known as clairaut's form. We should remember that this p stands for dy dx, and whenever we differentiate this equation with respect to x, we get dy dx equal to p plus x dp dx plus f prime p into dp dx. Since dy dx is nothing but p, they cancels out, and we have dp dx into x plus f prime p is equal to 0. So we have two options: either p is independent of x, that means p is a constant, otherwise x is equal to minus f prime. So from this relation we get y equal to cx plus fc as the general solution of this equation, isn't it so? And that is why this form is so special. Just replace p by c and you get the general solution of this nonlinear equation. Why? If from this relation we eliminate p from 1, using the relation 2 we eliminate p from 1, so we have a p eliminant where a relation between x and y is obtained. And similarly, if using this relation we eliminate c and we have a c eliminant, psi xy equal to 0, then the common part of these two gives us a singular solution which doesn't conform to the family of this general solution. I hope I have been able to explain thing. I repeat, this is a special form of nonlinear equation y equal to px plus fp, a so-called linear structure in terms of y and x, but dy dx is of any power, so this is nonlinear. And straight away we can find a general solution replacing p by c due to this calculation. And if we use this to eliminate p from these two, we have a other relation phi xy. And if we eliminate c from here, we have a c eliminant. Sometimes we see c discriminant. Just for as an example, if this is a quadratic in c, then we can use the c discriminant or find the c discriminant using the famous relation b square equal to 4ac. Isn't it so? If let this is a form like this, c square plus ac plus b. So this is a A and B are function of x and y both, and we can easily find the C discriminant as b square equal to 4a, isn't it so? So let us explain it with the help of a typical example. Okay, let us illustrate this idea of singular solution and clairaut's form using a particular example.